Alright, with this video we want to get into a little bit more detail about how a loop of wire can rotate and how you can affect its rotation inside of a magnetic field. As we talked about, a current carrying conductor in a magnetic field will experience a force. If you form that conductor into a loop, then half of the loop will experience a force in one direction, and the other half will experience a force in the other direction. So basically what you get is a rotation. To figure out the specifics of that rotation, you would need to use what's called the left-hand rule, and we're going to get to that later in this video. So for now, we're going to talk about the factors that affect the strength of rotation or the speed of this rotation. Okay, we'll start with simple ones, and then we'll look at the more interesting one third. So there's three of them. Let's start with the first two. All right, here they are. So they're pretty straightforward in all honesty, so that's why there's no diagram on this picture. The first thing is that you could increase the amount of current in the wire. Basically, the wire is being supplied with current from a power supply, so if you increase the current coming from the power supply, then you increase the current in the wire. That's going to in turn make the magnetic field around the wire stronger, which means a stronger interaction with your permanent magnet, and that's going to basically be a faster spin or a stronger force. All right. Secondly, you could increase the strength of that permanent magnetic field. Basically, what you need to do if you're using permanent magnets is get stronger permanent magnets and stick them in place of the magnets that you were previously using. The other thing that you can do, and this is what is more commonly done in actual, like, real motors that you would buy from the store or that you would use in a factory or whatever, oftentimes the permanent magnetic field is produced not by actual permanent magnets but by electromagnets. So then those electromagnets are controlled by a separate power supply usually, and then you can vary the strength of those just by varying the current in those permanent electromagnets, semi-permanent. I mean, obviously you can turn them off, but they act as the permanent magnetic field in which your coil of wire is rotating. So basically, if you increase the magnetic field strength of your permanent magnets, then the force experienced by the wire will be greater, and then the rotation will be faster also. All right, so basically increase the current in the wire, increase the strength of the magnetic field. That's two ways to change the rotation or make it faster. The third is the more interesting one, and it involves increasing the number of loops of wire in your coil. So basically, instead of just a loop, now we have a coil. It comes in at the top here and rotates, spins, it's all wound around something, and then it comes out the bottom there. So this coil of wire then, each of the loops experiences that force that we were talking about. So each of the loops is going to be rotating right along with all the others. So you get a really nice amplification of the effect, because each one of these single loops of wire experiences the same as all the others. So it adds up. All that force adds up to more rotation and faster spinning. So in practicality, engineers try to coil as much wire as possible into their motor, and this is an example of an actual motor, the inside of it, that you might purchase at the store. So you can see they've coiled a bunch of wire in here, and in fact this one has 3 separate coils of wire, which is another thing that engineers actually do in order to try to make motors more efficient. They don't just use one coil of wire, they'll use 3 or even 6 or 10, or depends on the motor. But that gets more complicated than what we need to know specifically for this course, because it really complicates things right in here. We'll talk about that in the next video. But just know that engineers that make real motors, they try to coil as much wire as possible in order to magnify and maximize the rotation effect that they get from that coil. Next, let's talk really quick about the left-hand rule. All right, so here we have the left-hand rule, the left-hand motor rule. Sometimes it's called Fleming's left-hand rule. This is what's going to let you figure out easily which direction the coil of wire is going to spin. in a particular situation. So I've set this up to match my diagram here. Basically, you're going to take your left hand and you're going to do this, 3-axis thing like we've done once before. I think we were using the right hand the last time we did this, but this one, for the motor, you have to use your left hand, okay? Have to use your left hand. Has to be left. Has to be left. Otherwise, it doesn't work right. Okay? So, you got your thumb is going to point straight up from your hand. Your finger is going to point out 90 degrees to your thumb, and then your second finger points out 90 degrees to both of them. Just like this. So, how does this work? Well, your first finger, F, points in the direction of the magnetic field. So, first finger, field. Thumb points in the direction of thrust, thrust or motion or force experienced by that part of the coil. And then your second finger points in the direction of the current. So second current, it's a little bit, that's the oddball out in terms of the mnemonic, right? So first finger, field, that matches. Thumb, thrust, that matches. Second finger, current. Okay? So how's that work? Well, the magnetic field is going this direction here. I'll just draw in a little arrow so we can see that from north to south. That's the magnetic field. Okay, so your first finger points that direction, and then bam, like that. Do it with me. Point your first finger that way on your left hand. Your thumb, point it up, and then we're going to look first at this half because it's really convenient. Current is going this direction, out of the screen, so point your middle finger out of the screen, and your thumb should be pointed up, which means that this side of the coil will go up. Now, you're going to have to flip your hand over to do the other side, because keeping the same orientation of your fingers, right? Thumb, field, current. The field stays the same, so you have to keep your first finger pointed in the same direction. But the current is going in now, so you need to point your middle finger in toward the screen, and that should result in your thumb pointing downwards. Okay? If you keep everything correct, in the correct orientation, then for this side, your thumb should be pointed downwards on that half of the coil of wire. So this wire would rotate in this direction, right, which is clockwise. So clockwise rotation as it sits right now, without adding the further complication. We have left out a very key detail that goes in this region of the motor, and we're going to add that in the next video. But for now, this is what you need to know. Hope that was helpful, and we'll see you next time.